So for the actual code, we again have the same structure of the files which I have provided in MATLAB, Python and Julia. So we have our shape function library, our solver, our mesh reader, and we actually have a driver which will assemble all of these files. And then we also have a post processing which will export to ParaView, and we'll be able to take a slice plot in ParaView, and we'll be able to visualize our solution and also export it and compare it again to our Excel sheet. Okay, so let's just do this quickly, and let me just run through the procedure. So the first is really the analogy which we talked about. How do we read the mesh? So this is really simple, no need to really go through it. There is nothing related to finite elements here. So this is really just reading the Gmesh export file. And so this is your Gmesh export file, right? So this is total number of nodes, and you have these, so each node, right? You have the XYZ coordinates of each node. And this is followed by triangles, which are your boundary elements, and then you will have tetrahedrons as well, which will be your internal elements, right? So really the mesh reader is just reading this data, right? Text. So the mesh reader is just doing something very similar to the 2D case. So in case of 2D, we just had triangles and lines here. So now we have text and triangles. Okay, so it just reads this mesh, whether it is a first order mesh or a second order mesh, and then it will just give you a mesh struct, right? Very similar to the 2D case, which will give you your element to node connectivity list, which will give you the total number of, which will give you your nodes at the boundaries, right? It will give you your element boundaries, I'm sorry, boundary elements and your inner elements, right? So all of this data will be provided by this mesh file. And now we come to our shape function library. So in shape function library, these are our shape functions, very simple. So we have already derived them. Again, we use the partition of unity and Kronecker delta property. And in case of the tetrahedron, linear tetrahedron, it's really simple. In case of triangle, we had just two directions. So we had three shape functions, psi, eta, and 1 minus psi minus eta. In case of tetrahedrons, we just extend that. And I have already shown it in the previous sessions, how we do this. And just by solving three equations for three unknowns, you can just get all of these four, and they are very similar to the triangle case. Here just we have a third direction, which is zeta, which is along the z direction, and so you have your four shape functions. The first one is 1 minus psi minus eta minus zeta. Okay, so you just have to be careful about the volume and that you are scaling the volume correctly, and that's about it. I mean, really very simple. Again, you can just take the derivatives along the psi, eta and zeta direction, right? And these are your derivatives. And this shape function file which I have provided, it's more of slightly more complex file, in which you also can change the order of integration, and you can also choose the element type. But here I have really given just one element type, that is triangles, but you could also put bricks into this if you want. And I have put order, and I have provided two options for order 1 and order 2, which is linears and quadratics. So in case of quadratics, really you will have to adapt your Gmesh file a bit, but in case of linears, it will just run very smoothly. So let's just use linears straightforwardly, and let's do the analysis. And what we are doing here is really we are also taking giving out the inputs in terms of your actual derivatives computed at the Gauss points, right? So this is slightly different than the live 2D solver, in which we did not do any pre-computation at the Gauss point. So here we are doing pre-computation. So to understand that, let's go to the Poisson solver. So we have looked at these two files, shape library and the mesh file. So now really the crucial file which is left is just the solver file. So let's go to the solver file. And in the solver file, we have a workflow. First we assemble the stiffness matrix, Then we identify those nodes, which are your boundary nodes, which are your directlet nodes, and then you just apply your Robin boundary condition at the Robin nodes, and also apply the directlet boundary condition, and then you solve. So this is your workflow. And for this, of course, I have defined some helper functions, and the helper function is the crucial one, is your assemble Laplace, which is basically assembling your stiffness matrix K. Okay, so this is the crux of whatever we did in the live coding. And this is slightly different, that here you are getting this guy here. So you are calling your shape function library before your actual loop. Okay, so this is what we call as pre-computations. So in the live coding, we actually called our shapes directly here inside. So this is superfluous because you are just calculating again and again. Don't need to do that. The Gauss points are fixed. So you're just mapping everything to the master element. So for the master element, you just derive these derivatives at the Gauss points, and then you just call these vectors here, right? Once again. So very similar. Here first we read our mesh file, right? Our elements. So this is our mesh to node connectivity. Element to node connectivity list. These are the pre-computations at the Gauss points. And then we just pre-allocate triplets here. So this is a triplet assembly, sparse assembly. This will allow us to run larger meshes, because in the live coding I did not do a sparse assembly, which uses spalloc kind of command, or triplet assembly. So those are the two ways to do this in MATLAB. And in case of Python and Julia also, I'm not aware if there is a spalloc kind of command, but you can do these triplet assemblies anyways. And these help you to run the solver to much higher kind of mesh densities. So that's the structure we have used here. Instead of starting rather pre-allocating a big matrix, we just allocate triplets, and then just we compute the Jacobian. So here we have not defined a helper function for that. So you can see it's very simple. We just call the connectivity list for the mesh IDs for a certain element. So we are just passing through element 1, element 2, and so on. We go to the connectivity list, call for the first element, we grab the nodes. For those nodes, we grab the x, y, z coordinates. Then we just do this multiplication to give our Jacobian of transformation. Take the derivative, take the inverse, and calculate your gradients. And these guys are, of course, your pre-computed ones, right? dn d psi, dn d eta. So these are your shape functions at the Gauss point, right? Right. So as you can see here, there is no Gauss loop here, and that is because these are vectors. Okay, so this is vectorized. So this code is basically vectorized instead of using Gauss points. So you just are multiplying with the Gauss weight here. Okay, and you are just running this over I and j, which are basically just your stiffness matrix rows and columns. So I refers to your test function, j refers to your trial function. So very simple code. And again, you can see the same kind of structure, the shape function derivative multiplied by its transpose in the x, y, and z direction. Very simple, very similar. Again, assemble them into triplets, and this is your sparse triplet assembly for your stiffness matrix. And then in your driver, again, you just so this is your helper function, right? So before we go to the driver, we have to assemble the boundary conditions. So for the directlet case, this is really very simple, exactly like we did in 2D. This is a strong imposition of boundary condition. In case of Robin condition, this will be complex. So this guy is really big, right? But it's really the same analogy. So we have just taken Gauss rule for a triangle, and we have just pulled in the x, y, z coordinates, and we could do a very detailed isoparametric mapping if we wanted, but here I have just used a shortcut hack. I have just taken the area, and we really don't need any derivatives here. If we needed the derivatives, we could have just done the entire isoparametric mapping, but here really we are just interested in multiplying the two shape functions here. Again, like the outer product, the shape function multiplied by the transpose. So this guy is your test node, your test function. This guy is your trial function. Okay, test multiplied by trial will give you your assembly, and this assembly goes into the stiffness matrix assembly. So this is your boundary assembly, boundary integral assembly. This goes into your this gets added into your stiffness matrix to give you a Robin contribution. And this is pretty much it. This is your Poisson solver or your Laplace solver, you could say. And in your driver, which is the final one, which we have to study now. So this is just very simple. You just define the test case. So you're just plugging in the Gmesh file which you want. If you want a diffusion coefficient, if you can plug it here as well. The Dirichlet boundary at the inner boundary, the flags. Read the mesh, solve, post process. That's it. So this is really simple, and let's just do this step by step. And for doing this, we'll have to generate a file in a mesh file in Gmesh. So let's just start off with that, and let's plug it into this code, run it, extract the data on ParaView, and compare with our analytical solution.